Alternating current. AC voltage applied to a resistor. Figure shows a resistor connected to a source epsilon of AC voltage. The symbol for an AC source in a circuit diagram is sine wave. We consider a source which produces sinusoidally varying potential difference across its terminals. Let this potential difference, also called AC voltage, be given by V is equal to Vm sin omega t, equation 1, where Vm is the amplitude of the oscillating potential difference and omega is its angular frequency. To find the value of current through the resistor, we apply Kirchhoff's loop rule. Summation omega of t is equal to 0 to the circuit shown in figure to get Vm sin omega t is equal to IR, or I is equal to Vm upon R sin omega t. Since R is a constant, we can write this equation as I is equal to Im sin omega t, equation 2, where the current amplitude Im is given by Im is equal to Vm upon R. Equation 3 is just Ohm's law, which for resistors works equally well for both AC and DC voltages. The voltage across a pure resistor and the current through it, given by equations 1 and 2, are plotted as a function of time in figure. Note in particular that both V and I reach 0, minimum and maximum values at the same time. Clearly, the voltage and current are in phase with each other. We see that, like the applied voltage, the current varies sinusoidally and has corresponding positive and negative values during each cycle. Thus, the sum of the instantaneous current values over one complete cycle is 0 and the average current is 0. The fact that the average current is 0, however, does not mean that the average power consumed is 0 and that there is no dissipation of electrical energy. As you know, Joule heating is given by I square R and depends on I square, which is always positive whether I is positive or negative and not on I. Thus, there is Joule heating and dissipation of electrical energy when an AC current passes through a resistor. The instantaneous power dissipated in the resistor is P is equal to I square R is equal to Im square R sin square omega t, equation 4. The average value of P over a cycle is P bar is equal to average of I square R is equal to average of Im square R sin square omega t, equation 5a, where the bar over a letter, here P, denotes its average value and this denotes taking average of the quantity inside the bracket. Since Im square and R are constants, P bar is equal to Im square R average of sin square omega t, equation 5b. Using the trigonometric identity, sin square omega t is equal to 1 upon 2, 1 minus cos 2 omega t. We have average of sin square omega t is equal to 1 upon 2, 1 minus average of cos 2 omega t. Since average of cos 2 omega t is equal to 0, we have average of sin square omega t is equal to 1 upon 2. Thus, P bar is equal to 1 upon 2 Im square R, equation 5c. To express AC power in the same form as DC power, which is P is equal to I square R, a special value of current is defined and used. It is called root mean square, that is RMS or effective current, and is denoted by I RMS or I. The average value of a function f of t over a period t is given by average of f of t is equal to 1 upon t integration 0 to t f of t dt. Average of cos 2 omega t is equal to 1 upon t integration 0 to t cos 2 omega t dt is equal to 1 upon t sin 2 omega t upon 2 omega 0 to t is equal to 1 upon 2 omega t sin 2 omega t minus 0 is equal to 0. It is defined by I is equal to square root of I square bar is equal to square root of 1 upon 2 Im square is equal to Im upon root 2 is equal to 0.707 Im. Equation 6. In terms of I, the average power denoted by P is equal to P bar is equal to 1 upon 2 Im square R is equal to I square R. Equation 7. Similarly, we define the root mean square voltage or effective voltage by V is equal to Vm upon root 2 is equal to 0.707 Vm. Equation 8. From equation 3, we have Vm is equal to Imr or Vm upon root 2 is equal to Im upon root 2 R or V is equal to IR. Equation 9 gives the relation between AC current and AC voltage and is similar to that in the DC case. This shows the advantage of introducing the concept of root mean square values. In terms of root mean square values, the equation for power and relation between current and voltage in AC circuits are essentially the same as those for the DC case. It is customary to measure and specify root mean square values for AC quantities. For example, the household line voltage of 220 volt is an root mean square value with a peak voltage of Vm is equal to root 2 V is equal to 1.414 into 220 volt is equal to 311 volt. In fact, the I or root mean square current is the equivalent DC current that would produce the same average power loss as the alternating current. Equation 7 can also be written as P is equal to V square upon R is equal to IV since V is equal to IR. Example 1. A light bulb is rated at 100 watt for a 220 volt supply. Find A. The resistance of the bulb, B. The peak voltage of the source, and C. The root mean square current through the bulb. Solution A. We are given P is equal to 100 watt and V is equal to 220 volt. The resistance of the bulb is R is equal to V square upon P is equal to 220 volt whole square upon 100 watt is equal to 484 ohm. B. The peak voltage of the source is Vm is equal to root 2 V is equal to 311 volt. C. Since P is equal to IV, I is equal to P upon V is equal to 100 watt upon 220 volt is equal to 0.454 ampere. Number 3. Representation of AC current and voltage by rotating vectors, phasors. The current through a resistor is in phase with the AC voltage, but this is not so in the case of an inductor, a capacitor, or a combination of these circuit elements. In order to show phase relationship between voltage and current in an AC circuit, we use the notion of phasors. The analysis of an AC circuit is facilitated by the use of a phasor diagram. A phasor is a vector which rotates about the origin with angular speed omega, as shown in figure. The vertical components of phasors V and I represent the sinusoidally varying quantities V and I. The magnitudes of phasors V and I represent the amplitudes or the peak values Vm and Im of these oscillating quantities. Figure shows the voltage and current phasors and their relationship at time t1 for the case of an AC source connected to a resistor, that is, corresponding to the circuit shown in figure. The projection of voltage and current phasors on vertical axis, that is, Vm sin omega t and Im sin omega t respectively, represent the value of voltage and current at that instant. As they rotate with frequency omega, curves in figure are generated. From figure, we see that phasors V and I for the case of a resistor are in the same direction. This is so for all times. This means that the phase angle between the voltage and the current is 0. Number 4. AC voltage applied to an inductor. Figure shows an AC source connected to an inductor. Usually, inductors have appreciable resistance in their windings, but we shall assume that this inductor has negligible resistance. Thus, the circuit is a purely inductive AC circuit. Let the voltage across the source be V is equal to Vm sin omega t. Using the Kirchhoff's loop rule, summation epsilon of t is equal to 0, and since there is no resistor in the circuit, V minus L di upon dt is equal to 0, equation 10, where the second term is the self-induced Faraday electromotive force in the inductor and L is the self-inductance of the inductor. The negative sign follows from Lenz's law. Combining equation 1 and 10, we have di upon dt is equal to V upon L is equal to Vm upon L sin omega t, equation 11. Equation 11 implies that the equation for I of t, the current as a function of time, must be such that its slope di upon dt is a sinusoidally varying quantity with the same phase as the source voltage and an amplitude given by Vm upon L. To obtain the current, we integrate di upon dt with respect to time. Integration di upon dt into dt is equal to Vm upon L integration sin omega t dt. I is equal to minus Vm upon omega L cos omega t plus constant. The integration constant has the dimension of current and is time independent. Since the source has an electromotive force which oscillates symmetrically about 0, the current it sustains also oscillates symmetrically about 0, so that no constant or time independent component of the current exists. Therefore, the integration constant is 0. Using minus cos omega t is equal to sin omega t minus pi by 2, we have I is equal to Im sin omega t minus pi by 2, equation 12, where Im is equal to Vm upon omega L is the amplitude of the current. The quantity omega L is analogous to the resistance and is called inductive reactance, denoted by XL. XL is equal to omega L, equation 13. The amplitude of the current is, then Im is equal to Vm upon omega L, equation 14. The dimension of inductive reactance is the same as that of resistance and its SI unit is ohm. The inductive reactance limits the current in a purely inductive circuit in the same way as the resistance limits the current in a purely resistive circuit. The inductive reactance is directly proportional to the inductance and to the frequency of the current. A comparison of equations 1 and 12 for the source voltage and the current in an inductor shows that the current lags the voltage by pi by 2 or 1/4 cycle. Figure shows the voltage and the current phasors in the present case at instant t1. The current phasor I is pi by 2 behind the voltage phasor V. When rotated with frequency omega counterclockwise, they generate the voltage and current given by equations 1 and 12 respectively, and as shown in figure. We see that the current reaches its maximum value later than the voltage by 1/4 of a period. T upon 4 is equal to pi by 2 upon omega. You have seen that an inductor has reactance that limits current similar to resistance in a DC circuit. Does it also consume power like a resistance? Let us try to find out. The instantaneous power supplied to the inductor is PL is equal to IV is equal to Im sin omega t minus pi by 2 into Vm sin omega t is equal to minus Im Vm cos omega t sin omega t is equal to minus Im Vm upon 2 sin 2 omega t. So, the average power over a complete cycle is PL is equal to average of minus Im Vm upon 2 sin 2 omega t is equal to minus Im Vm upon 2 average of sin 2 omega t is equal to 0, since the average of sin 2 omega t over a complete cycle is 0. Thus, the average power supplied to an inductor over one complete cycle is 0. Example 2. A pure inductor of 25.0 millihenry is connected to a source of 220 volt. Find the inductive reactance and root mean square current in the circuit if the frequency of the source is 50 Hz. Solution. The inductive reactance XL is equal to 2 pi nu L is equal to 2 into 3.14 into 50 into 25 into 10 raised to minus 3 ohm is equal to 7.85 ohm. The root mean square current in the circuit is I is equal to V upon XL is equal to 220 volt upon 7.85 ohm is equal to 28 ampere. 0 to 1 current I through the coil entering at A increase from 0 to a maximum value. Flux lines are set up, that is, the core gets magnetized. With the polarity shown, voltage and current are both positive, so their product P is positive. Energy is absorbed from the source. 1 to 2 current in the coil is still positive but is decreasing. The core gets demagnetized and the net flux becomes 0 at the end of a half cycle. The voltage V is negative since di upon dt is negative. The product of voltage and current is negative and energy is being returned to source. 2 to 3 current I becomes negative, that is, it enters at B and comes out of A. Since the direction of current has changed, the polarity of the magnet changes. The current and voltage are both negative, so their product P is positive. Energy is absorbed. 3 to 4 current I decreases and reaches its zero value at 4 when core is demagnetized and flux is 0. The voltage is positive but the current is negative. The power is therefore negative. Energy absorbed during the 1/4 cycle 2 to 3 is returned to the source. AC voltage applied to a capacitor. Figure shows an AC source epsilon generating AC voltage V is equal to Vm sin omega t connected to a capacitor only, a purely capacitive AC circuit. When a capacitor is connected to a voltage source in a DC circuit, current will flow for the short time required to charge the capacitor. As charge accumulates on the capacitor plates, the voltage across them increases, opposing the current. That is, a capacitor in a DC circuit will limit or oppose the current as it charges. When the capacitor is fully charged, the current in the circuit falls to zero. When the capacitor is connected to an AC source, as in figure, it limits or regulates the current, but does not completely prevent the flow of charge. The capacitor is alternately charged and discharged as the current reverses each half cycle. Let Q be the charge on the capacitor at any time t. The instantaneous voltage V across the capacitor is V is equal to Q upon C, equation 15. From the Kirchhoff's loop rule, the voltage across the source and the capacitor are equal. Vm sin omega t is equal to Q upon C. To find the current, we use the relation I is equal to dq upon dt. I is equal to d upon dt Vm C sin omega t is equal to omega C Vm cos omega t. Using the relation cos omega t is equal to sin omega t plus pi by 2, we have I is equal to Im sin omega t plus pi by 2, equation 16, where the amplitude of the oscillating current is Im is equal to omega C Vm. We can rewrite it as Im is equal to Vm upon 1 upon omega C. Comparing it to Im is equal to Vm upon R for a purely resistive circuit, we find that 1 upon omega C plays the role of resistance. It is called capacitive reactance and is denoted by Xc. Xc is equal to 1 upon omega C, equation 17. So that the amplitude of the current is Im is equal to Vm upon Xc, equation 18. The dimension of capacitive reactance is the same as that of resistance and its SI unit is ohm. The capacitive reactance limits the amplitude of the current in a purely capacitive circuit in the same way as the resistance limits the current in a purely resistive circuit, but it is inversely proportional to the frequency and the capacitance. A comparison of equation 16 with the equation of source voltage, equation 1 shows that the current is pi by 2 ahead of voltage. Figure shows the phasor diagram at an instant t1. Here the current phasor I is pi by 2 ahead of the voltage phasor V as they rotate counterclockwise. Figure shows the variation of voltage and current with time. We see that the current reaches its maximum value earlier than the voltage by 1/4 of a period. The instantaneous power supplied to the capacitor is Pc is equal to IV is equal to Im cos omega t Vm sin omega t is equal to Im Vm cos omega t sin omega t is equal to Im Vm upon 2 sin 2 omega t, equation 19. So, as in the case of an inductor, the average power Pc is equal to average of Im Vm upon 2 sin 2 omega t is equal to Im Vm upon 2 average of sin 2 omega t is equal to 0. Since average of sin 2 omega t is equal to 0 over a complete cycle, figure explains it in detail. Thus, in the case of an inductor, the current lags the voltage by pi by 2, and in the case of a capacitor, the current leads the voltage by pi by 2. Example 3. A lamp is connected in series with a capacitor. Predict your observations for DC and AC connections What happens in each case if the capacitance of the capacitor is reduced? Solution: when a DC source is connected to a capacitor, the capacitor gets charged, and after charging, no current flows in the circuit and the lamp will not glow. There will be no change even if C is reduced. With AC source, the capacitor offers capacitative reactance 1 upon omega C and the current flows in the circuit. Consequently, the lamp will shine. Reducing C will increase reactance and the lamp will shine less brightly than before. Example 4. A 15.0 microfarad capacitor is connected to a 220 volt 50 Hz source. Find the capacitive reactance and the current, that is, root mean square and peak in the circuit. If the frequency is doubled, what happens to the capacitive reactance and the current? Solution: the capacitive reactance is Xc is equal to 1 upon 2 pi Vc is equal to 1 upon 2 pi into 50 Hz into 15.0 into 10 raised to minus 6 farad is equal to 212 ohm. The root mean square current is 0 to 1. The current I flows as shown and from the maximum at 0 reaches a 0 value at 1. The plate A is charged to positive polarity while negative charge Q builds up in B reaching a maximum at 1 unit. The current becomes 0. The voltage Vc is equal to Q upon C is in phase with Q and reaches maximum value at 1. Current and voltage are both positive. So, P is equal to Vci is positive. Energy is absorbed from the source during this quarter cycle as the capacitor is charged. 1 to 2, the current I reverses its direction. The accumulated charge is depleted, that is, the capacitor is discharged during this quarter cycle. The voltage gets reduced but is still positive. The current is negative. Their product, the power, is negative. The energy absorbed during the 1 quarter cycle 0 to 1 is returned during this quarter. 2 to 3, as I continues to flow from A to B, the capacitor is charged to reversed polarity, that is, the plate B acquires positive and A acquires negative charge. Both the current and the voltage are negative. Their product P is positive. The capacitor absorbs energy during this 1 quarter cycle. 3 to 4, the current I reverses its direction at 3 and flows from B to A. The accumulated charge is depleted and the magnitude of the voltage Vc is reduced. Vc becomes 0 at 4 when the capacitor is fully discharged. The power is negative. Energy absorbed during 2 to 3 is returned to the source. Net energy absorbed is 0. I is equal to V upon Xc is equal to 220 volt upon 212 ohm is equal to 1.04 ampere. The peak current is Im is equal to root 2 I is equal to 1.41 into 1.04 is equal to 1.47 ampere. This current oscillates between plus 1.47 ampere and minus 1.47 ampere and is ahead of the voltage by pi by 2. If the frequency is doubled, the capacitive reactance is halved and consequently the current is doubled. Example 5. A light bulb and an open coil inductor are connected to an AC source through a key as shown in figure. The switch is closed and after some time an iron rod is inserted into the interior of the inductor. The glow of the light bulb A increases, B decreases, C is unchanged as the iron rod is inserted. Give your answer with reasons. Solution. As the iron rod is inserted, the magnetic field inside the coil magnetizes the iron, increasing the magnetic field inside it. Hence, the inductance of the coil increases. Consequently, the inductive reactance of the coil increases. As a result, a large fraction of the applied AC voltage appears across the inductor, leaving less voltage across the bulb. Therefore, the glow of the light bulb decreases. AC voltage applied to a series LCR circuit. Figure shows a series LCR circuit connected to an AC source epsilon. As usual, we take the voltage of the source to be V is equal to Vm sin omega t. If Q is the charge on the capacitor and I the current at time t, we have from Kirchhoff's loop rule L di upon dt plus IR plus Q upon C is equal to V, equation 20. We want to determine the instantaneous current I and its phase relationship to the applied alternating voltage V. We shall solve this problem by two methods. First, we use the technique of phasors, and in the second method, we solve equation 20 analytically to obtain the time dependence of I. Phasor diagram solution. From the circuit shown in figure, we see that the resistor, inductor and capacitor are in series. Therefore, the AC current in each element is the same at any time, having the same amplitude and phase. Let it be I is equal to Im sin omega t plus phi, equation 21, where phi is the phase difference between the voltage across the source and the current in the circuit. On the basis of what we have learnt in the previous sections, we shall construct a phasor diagram for the present case. Let I be the phasor representing the current in the circuit as given by equation 21. Further, let VL, VR, VC and V represent the voltage across the inductor, resistor, capacitor and the source respectively. We know that VR is parallel to I. VC is pi by 2 behind I and VL is pi by 2 ahead of I. VL, VR, VC and I are shown in figure with appropriate phase relations. The length of these phasors or the amplitude of VR, VC and VL are VRM is equal to IMR, VCM is equal to IMXC, VLM is equal to IMXL. Equation 22. The voltage equation 20 for the circuit can be written as VL plus VR plus VC is equal to V. Equation 23. The phasor relation whose vertical component gives the above equation is VL plus VR plus VC is equal to V. Equation 24. This relation is represented in figure. Since VC and VL are always along the same line and in opposite directions, they can be combined into a single phasor, that is VC plus VL, which has a magnitude VCM minus VLM. Since V is represented as the hypotenuse of a right triangle whose sides are VR and VC plus VL, the Pythagorean theorem gives Vm square is equal to VRM square plus VCM minus VLM whole square. Substituting the values of VRM, VCM and VLM from equation 22, VRM is equal to IMR, VCM is equal to IMXC, VLM is equal to IMXL. Into the above equation, we have Vm square is equal to IMR whole square plus IMXC minus IMXL whole square. Vm square is equal to Im square into R square plus Xc minus XL whole square. Or Im is equal to Vm upon square root of r square plus xc minus xl whole square. Equation 25a. By analogy to the resistance in a circuit, we introduce the impedance Z in an AC circuit. Im is equal to Vm upon Z. Equation 25b, where Z is equal to square root of r square plus xc minus xl whole square. Equation 26. Since phasor I is always parallel to phasor VR, the phase angle phi is the angle between VR and V and can be determined from figure. Tan phi is equal to VCM minus VLM upon VRM. Using equation 22, we have tan phi is equal to XC minus XL upon R. Equation 27. Equations 26 and 27 are graphically shown in figure. This is called impedance diagram, which is a right triangle with Z as its hypotenuse. Equation 25a gives the amplitude of the current and equation 27 gives the phase angle. With this, equation 21 is completely specified. If Xc is greater than XL, phi is positive and the circuit is predominantly capacitive. Consequently, the current in the circuit leads the source voltage. If Xc is less than XL, phi is negative and the circuit is predominantly inductive. Consequently, the current in the circuit lags the source voltage. Figure shows the phasor diagram and variation of V and I with omega t for the case Xc is greater than XL. Thus, we have obtained the amplitude and phase of current for an LCR series circuit using the technique of phasors. But this method of analyzing AC circuits suffers from certain disadvantages. First, the phasor diagrams say nothing about the initial condition. One can take any arbitrary value of t, say t1, and draw different phasors which show the relative angle between different phasors. The solution so obtained is called the steady-state solution. This is not a general solution. Additionally, we do have a transient solution which exists even for V is equal to 0. The general solution is the sum of the transient solution and the steady-state solution. After a sufficiently long time, the effects of the transient solution die out and the behavior of the circuit is described by the steady-state solution. Analytical solution. The voltage equation for the circuit is L di upon dt plus Ri plus Q upon C is equal to V is equal to Vm sin omega t. We know that I is equal to dq upon dt. Therefore, di upon dt is equal to d square q upon dt square. Thus, in terms of q, the voltage equation becomes L d square q upon dt square plus R dq upon dt plus q upon C is equal to Vm sin omega t. Equation 28. This is like the equation for a forced, damped oscillator. Let us assume a solution Q is equal to Qm sin omega t plus theta. Equation 29a. So that dq upon dt is equal to Qm omega cos omega t plus theta. Equation 29b. And d square q upon dt square is equal to minus Qm omega square sin omega t plus theta. Equation 29c. Substituting these values in equation 28, we get Qm omega into R cos omega t plus theta plus Xc minus XL sin omega t plus theta is equal to Vm sin omega t. Equation 30, where we have used the relation Xc is equal to 1 upon omega c, XL is equal to omega L. Multiplying and dividing equation 30 by Z is equal to square root of R square plus Xc minus XL whole square, we have Qm omega Z into R upon Z cos omega t plus theta plus Xc minus XL upon Z sin omega t plus theta is equal to Vm sin omega t, equation 31. Now, let R upon Z is equal to cos phi and Xc minus XL upon Z is equal to sin phi, so that phi is equal to tan inverse Xc minus XL upon R, equation 32. Substituting this in equation 31 and simplifying, we get Qm omega Z cos omega t plus theta minus phi is equal to Vm sin omega t, equation 33. Comparing the two sides of this equation, we see that Vm is equal to Qm omega Z is equal to Im Z, where Im is equal to Qm omega, equation 33a, and theta minus phi is equal to minus pi by 2, or theta is equal to minus pi by 2 plus phi, equation 33b. Therefore, the current in the circuit is I is equal to dq upon dt is equal to Qm omega cos omega t plus theta is equal to Im cos omega t plus theta, or I is equal to Im sin omega t plus phi, equation 34, where Im is equal to Vm upon Z is equal to Vm upon square root of R square plus Xc minus XL whole square, equation 34a, and phi is equal to tan inverse Xc minus XL upon R. Thus, the analytical solution for the amplitude and phase of the current in the circuit agrees with that obtained by the technique of phasors. Resonance. The phenomenon of resonance is common among systems that have a tendency to oscillate at a particular frequency. This frequency is called the system's natural frequency. If such a system is driven by an energy source at a frequency that is near the natural frequency, the amplitude of oscillation is found to be large. A familiar example of this phenomenon is a child on a swing. The swing has a natural frequency for swinging back and forth like a pendulum. If the child pulls on the rope at regular intervals and the frequency of the pulls is almost the same as the frequency of swinging, the amplitude of the swinging will be large. For an RLC circuit driven with voltage of amplitude Vm and frequency omega, we found that the current amplitude is given by Im is equal to Vm upon Z is equal to Vm upon square root of R square plus Xc minus XL whole square, with Xc is equal to 1 upon omega C and XL is equal to omega L. So if omega is varied, then at a particular frequency omega 0, Xc is equal to XL and the impedance is minimum, that is Z is equal to square root of R square minus 0 square is equal to R. This frequency is called the resonant frequency. Xc is equal to XL, or 1 upon omega 0 C is equal to omega 0 L, or omega 0 is equal to 1 upon square root of LC, equation 35. At resonant frequency, the current amplitude is maximum. Im is equal to Vm upon R. Figure shows the variation of Im with omega in a RLC series circuit with L is equal to 1.00 millihenry, C is equal to 1.00 nanofarad. For two values of R, number 1, R is equal to 100 ohm and number 2, R is equal to 200 ohm. For the source applied, Vm is equal to 100 volt. Omega 0 for this case is 1 upon square root of LC is equal to 1.00 into 10 raised to 6 radian per second. We see that the current amplitude is maximum at the resonant frequency. Since Im is equal to Vm upon R, at resonance, the current amplitude for case 1 is twice to that for case 2. Resonant circuits have a variety of applications. For example, in the turning mechanism of a radio or a TV set, the antenna of a radio accepts signals from many broadcasting stations. The signals picked up in the antenna acts as a source in the turning circuit of the radio. So the circuit can be driven at many frequencies, but to hear one particular radio station, we tune the radio. In tuning, we vary the capacitance of a capacitor in the tuning circuit such that the resonant frequency of the circuit becomes nearly equal to the frequency of the radio signal received. When this happens, the amplitude of the current with the frequency of the signal of the particular radio station in the circuit is maximum. It is important to note that resonance phenomenon is exhibited by a circuit only if both L and C are present in the circuit. Only then do the voltages across L and C cancel each other, that is, both being out of phase. And the current amplitude is Vm upon R, the total source voltage appearing across R. This means that we cannot have resonance in a RL or RC circuit. Sharpness of resonance. The amplitude of the current in the series LCR circuit is given by Im is equal to Vm upon square root of R square plus omega L minus 1 upon omega C whole square, and is maximum when omega is equal to omega 0 is equal to 1 upon square root of LC. The maximum value is Im maximum is equal to Vm upon R. For values of omega other than omega 0, the amplitude of the current is less than the maximum value. Suppose we choose a value of omega for which the current amplitude is 1 upon root 2 times its maximum value. At this value, the power dissipated by the circuit becomes half. From the curve in figure, we see that there are two such values of omega, say omega 1 and omega 2, one greater and the other smaller than omega 0 and symmetrical about omega 0. We may write omega 1 is equal to omega 0 plus delta omega. Omega 2 is equal to omega 0 minus delta omega. The difference omega 1 minus omega 2 is equal to 2 delta omega is often called the bandwidth of the circuit. The quantity omega 0 upon 2 delta omega is regarded as a measure of the sharpness of resonance. The smaller the delta omega, the sharper or narrower is the resonance. To get an expression for delta omega, we note that the current amplitude Im is 1 upon root 2 Im maximum for omega 1 is equal to omega 0 plus delta omega. Therefore, at omega 1, Im is equal to Vm upon square root of R square plus omega 1 L minus 1 upon omega 1 C whole square is equal to Im maximum upon root 2 is equal to Vm upon R root 2, or square root of R square plus omega 1 L minus 1 upon omega 1 C whole square is equal to R root 2. R square plus omega 1 L minus 1 upon omega 1 C whole square is equal to 2R square. Omega 1 L minus 1 upon omega 1 C is equal to R, which may be written as omega 0 plus delta omega into L minus 1 upon omega 0 plus delta omega into C is equal to R. Omega 0 L into 1 plus delta omega upon omega 0 minus 1 upon omega 0 C into 1 plus delta omega upon omega 0 is equal to R, using omega 0 square is equal to 1 upon LC. In the second term on the left hand side, we get omega 0 L into 1 plus delta omega upon omega 0 minus omega 0 L upon 1 plus delta omega upon omega 0 is equal to R. We can approximate 1 plus delta omega upon omega 0 whole raised to minus 1 as 1 minus delta omega upon omega 0, since delta omega upon omega 0 much less than 1. Therefore, omega 0 L into 1 plus delta omega upon omega 0 minus omega 0 L into 1 minus delta omega upon omega 0 is equal to R, or omega 0 L 2 delta omega upon omega 0 is equal to R. Delta omega is equal to R upon 2L. Equation 36a. The sharpness of resonance is given by omega 0 upon 2 delta omega is equal to omega 0 L upon R. Equation 36b. The ratio omega 0 L upon R is also called the quality factor Q of the circuit. Q is equal to omega 0 L upon R. Equation 36c. From equations 36b and 36c, we see that 2 delta omega is equal to omega 0 upon Q. So larger the value of Q, the smaller is the value of 2 delta omega or the bandwidth, and sharper is the resonance. Using equation 36c can be equivalently expressed as Q is equal to 1 upon omega 0 CR. We see from figure that if the resonance is less sharp, not only is the maximum current less, the circuit is close to resonance. For a larger range, delta omega of frequencies and the turning of the circuit will not be good. So, less sharp the resonance, less is the selectivity of the circuit, or vice versa. From equation 36, we see that if quality factor is large, that is R is low or L is large, the circuit is more selective. Example 6. A resistor of 200 ohm and a capacitor of 15.0 microfarad are connected in series to a 220 volt 50 Hz AC source. A. Calculate the current in the circuit. B. Calculate the voltage, that is root mean square, across the resistor and the capacitor. Is the algebraic sum of these voltages more than the source voltage? If yes, resolve the paradox. Solution. Given R is equal to 200 ohm, C is equal to 15.0 microfarad is equal to 15.0 into 10 raised to minus 6 farad. V is equal to 220 volt. Nu is equal to 50 Hz. A. In order to calculate the current, we need the impedance of the circuit. It is Z is equal to square root of R square plus Xc square is equal to square root of R square plus 2 pi nu C whole raised to minus 2 is equal to square root of 200 ohm whole square plus 2 into 3.14 into 50 into 15.0 into 10 raised to minus 6 farad whole raised to minus 2 is equal to square root of 200 ohm whole square plus 212.3 ohm whole square is equal to 291.67 ohm. Therefore, the current in the circuit is I is equal to V upon Z is equal to 220 volt upon 291.67 ohm is equal to 0.7542 ampere. B. Since the current is the same throughout the circuit, we have VR is equal to IR is equal to 0.754 ampere into 200 ohm is equal to 150.8 volt. VC is equal to IXC is equal to 0.754 ampere into 212.3 ohm is equal to 160.07 volt. The algebraic sum of the two voltages VR and VC is 311.3 volt, which is more than the source voltage of 220 volt. The two voltages are not in the same phase. Therefore, they cannot be added like ordinary numbers. The two voltages are out of phase by 90 degrees. Therefore, the total of these voltages must be obtained using the Pythagorean theorem. VR plus C is equal to square root of VR square plus VC square is equal to 219.91 is approximately equal to 220 volt. Thus, if the phase difference between two voltages is properly taken into account, the total voltage across the resistor and the capacitor is equal to the voltage of the source. Power in AC circuit, the power factor. We have seen that a voltage V is equal to Vm sin omega t applied to a series RLC circuit drives a current in the circuit given by I is equal to Im sin omega t plus phi, where Im is equal to Vm upon Z and phi is equal to tan inverse Xc minus XL upon R. Therefore, the instantaneous power P supplied by the source is P is equal to Vi is equal to Vm sin omega t into Im sin omega t plus phi is equal to Vm Im upon 2 cos phi minus cos 2 omega t plus phi, equation 37. The average power over a cycle is given by the average of the two terms in right hand side of equation 37. It is only the second term which is time dependent. Its average is 0. That is, the positive half of the cosine cancels the negative half. Therefore, P is equal to Vm Im upon 2 cos phi is equal to Vm upon root 2 Im upon root 2 cos phi is equal to Vi cos phi, equation 38a. This can also be written as P is equal to I square Z cos phi, equation 38b. So, the average power dissipated depends not only on the voltage and current, but also on the cosine of the phase angle phi between them. The quantity cos phi is called the power factor. Let us discuss the following cases. Case 1. Resistive circuit. If the circuit contains only pure R, it is called resistive. In that case, phi is equal to 0, cos phi is equal to 1. There is maximum power dissipation. Case 2. Purely inductive or capacitive circuit. If the circuit contains only an inductor or capacitor, we know that the phase difference between voltage and current is pi by 2. Therefore, cos phi is equal to 0 and no power is dissipated even though a current is flowing in the circuit. This current is sometimes referred to as wattless current. Case 3. LCR series circuit. In an LCR series circuit, power dissipated is given by equation 38, where phi is equal to tan inverse Xc minus XL upon R. So, phi may be non-zero in a RL or RC or RCL circuit. Even in such cases, power is dissipated only in the resistor. Case 4. Power dissipated at resonance in LCR circuit. At resonance, Xc minus XL is equal to 0 and phi is equal to 0. Therefore, cos phi is equal to 1 and P is equal to I square Z is equal to I square R. That is, maximum power is dissipated in a circuit through R at resonance. Example 7a. For circuits used for transporting electric power, a low power factor implies large power loss in transmission. Explain. B. Power factor can often be improved by the use of a capacitor of appropriate capacitance in the circuit. Explain. Solution A. We know that P is equal to IV cos phi, where cos phi is the power factor. To supply a given power at a given voltage, if cos phi is small, we have to increase current accordingly. But this will lead to large power loss, that is I square R in transmission. B. Suppose in a circuit, current I lags the voltage by an angle phi, then power factor cos phi is equal to R upon Z. We can improve the power factor tending to 1 by making Z tend to R. Let us understand with the help of a phasor diagram how this can be achieved. Let us resolve I into two components, IP along the applied voltage V and IQ perpendicular to the applied voltage. IQ is called the wattless component since corresponding to this component of current, there is no power loss. IP is known as the power component because it is in phase with the voltage and corresponds to power loss in the circuit. It's clear from this analysis that if we want to improve power factor, we must completely neutralize the lagging wattless current IQ by an equal leading wattless current IQ dash. This can be done by connecting a capacitor of appropriate value in parallel so that IQ and IQ dash cancel each other and P is effectively IPV. Example 8. A sinusoidal voltage of peak value 283 volt and frequency 50 Hz is applied to a series LCR circuit in which R is equal to 3 ohm, L is equal to 25.48 millihenry and C is equal to 796 microfarad. Find A. The impedance of the circuit. B. The phase difference between the voltage across the source and the current. C. The power dissipated in the circuit. And D. The power factor. Solution A. To find the impedance of the circuit, we first calculate XL and XC. XL is equal to 2 pi nu L is equal to 2 into 3.14 into 50 into 25.48 into 10 raised to minus 3 ohm is equal to 8 ohm. XC is equal to 1 upon 2 pi nu C is equal to 1 upon 2 into 3.14 into 50 into 796 into 10 raised to minus 6 is equal to 4 ohm. Therefore, Z is equal to square root of R square plus XL minus XC whole square is equal to square root of 3 square plus 8 minus 4 whole square is equal to 5 ohm. B. Phase difference. Phi is equal to tan inverse XC minus XL upon R is equal to tan inverse 4 minus 8 upon 3 is equal to minus 53.1 degree. Since phi is negative, the current in the circuit lags the voltage across the source. C. The power dissipated in the circuit is P is equal to I square R. Now, I is equal to Im upon root 2 is equal to 1 upon root 2 into 283 upon 5 is equal to 40 ampere. Therefore, P is equal to 40 ampere whole square into 3 ohm is equal to 4800 watt. D. Power factor is equal to cos phi is equal to cos minus 53.1 degree is equal to 0.6. Example 9. Suppose the frequency of the source in the previous example can be varied. A. What is the frequency of the source at which resonance occurs? B. Calculate the impedance, the current, and the power dissipated at the resonant condition. Solution A. The frequency at which the resonance occurs is omega 0 is equal to 1 upon square root of LC is equal to 1 upon square root of 25.48 into 10 raised to minus 3 into 796 into 10 raised to minus 6 is equal to 222.1 radian per second. VR is equal to omega 0 upon 2 pi is equal to 222.1 upon 2 into 3.14 Hz is equal to 35.4 Hz. B. The impedance Z at resonant condition is equal to the resistance. Z is equal to R is equal to 3 ohm. The root mean square current at resonance is equal to V upon Z is equal to V upon R is equal to 283 upon root 2 into 1 upon 3 is equal to 66.7 ampere. The power dissipated at resonance is P is equal to I square into R is equal to 66.7 whole square into 3 is equal to 13.35 kilowatt. Example 10. At an airport, a person is made to walk through the doorway of a metal detector for security reasons. If she or he is carrying anything made of metal, the metal detector emits a sound. On what principle does this detector work? Solution: the metal detector works on the principle of resonance in AC circuits. When you walk through a metal detector, you are in fact walking through a coil of many tons. The coil is connected to a capacitor turned so that the circuit is in resonance. When you walk through with metal in your pocket, the impedance of the circuit changes, resulting in significant change in current in the circuit. This change in current is detected and the electronic circuitry causes a sound to be emitted as an alarm. LC oscillations. We know that a capacitor and an inductor can store electrical and magnetic energy respectively. When a capacitor initially charged is connected to an inductor, the charge on the capacitor and the current in the circuit exhibit the phenomenon of electrical oscillations similar to oscillations in mechanical systems. Let a capacitor be charged Qm at t is equal to 0 and connected to an inductor as shown in figure. The moment the circuit is completed, the charge on the capacitor starts decreasing, giving rise to current in the circuit. Let Q and I be the charge and current in the circuit at time t. Since di upon dt is positive, the induced electromotive force in L will have polarity as shown, that is, Vb is less than Va according to Kirchhoff's loop rule. Q upon C minus L di upon dt is equal to 0, equation 39. I is equal to minus dq upon dt. So, in the present case, as Q decreases, I increases. Therefore, equation 39 becomes d square Q upon dt square plus 1 upon LC Q is equal to 0, equation 40. This equation has the form d square x upon dt square plus omega 0 square x is equal to 0 for a simple harmonic oscillator. The charge therefore oscillates with a natural frequency. Omega 0 is equal to 1 upon square root of LC, equation 41, and varies sinusoidally with time as Q is equal to Qm cos omega 0 t plus phi, equation 42, where Qm is the maximum value of Q and phi is a phase constant. Since Q is equal to Qm at t is equal to 0, we have cos phi is equal to 1 or phi is equal to 0. Therefore, in present case, Q is equal to Qm cos omega 0 t, equation 43. The current I is equal to minus dq upon dt is given by I is equal to Im sin omega 0 t, equation 44, where Im is equal to omega 0 Qm. Let us now try to visualize how this oscillation takes place in the circuit. Figure shows a capacitor with initial charge Qm connected to an ideal inductor. The electrical energy stored in the charged capacitor is UE is equal to 1 upon 2 Qm square upon C. Since there is no current in the circuit, energy in the inductor is 0. Thus, the total energy of LC circuit is U is equal to UE is equal to 1 upon 2 Qm square upon C. At t is equal to 0, the switch is closed and the capacitor starts to discharge. As the current increases, it sets up a magnetic field in the inductor and thereby some energy gets stored in the inductor in the form of magnetic energy. UB is equal to 1 upon 2 Li square. As the current reaches its maximum value Im at t is equal to t upon 4 as in figure, all the energy is stored in the magnetic field UB is equal to 1 upon 2 Lim square. You can easily check the maximum electrical energy equals the maximum magnetic energy. The capacitor now has no charge and hence no energy. The current now starts charging the capacitor as in figure. This process continues till the capacitor is fully charged at T is equal to T upon 2, but it is charged with a polarity opposite to its initial state in figure. The whole process just described will now repeat itself till the system reverts to its original state. Thus, the energy in the system oscillates between the capacitor and the inductor. The LC oscillation is similar to the mechanical oscillation of a block attached to a spring. The lower part of each figure in figure depicts the corresponding stage of a mechanical system, that is, a block attached to a spring. For a block of a mass m oscillating with frequency omega 0, the equation is d square x upon dt square plus omega 0 square x is equal to 0. Here omega 0 is equal to square root of k upon m, and k is the spring constant, so x corresponds to q. In case of a mechanical system, F is equal to ma is equal to m into dv upon dt is equal to m into d square x upon dt square. For an electrical system, epsilon is equal to minus L into di upon dt is equal to minus L into d square q upon dt square. Comparing these two equations, we see that L is analogous to mass, m is to L is a measure of resistance to charge in current. In case of LC circuit, omega 0 is equal to 1 upon square root of LC, and for mass on a spring, omega 0 is equal to square root of k upon m. So, 1 upon c is analogous to k. The constant k is equal to F upon x tells us the external force required to produce a unit displacement, whereas 1 upon c is equal to V upon q tells us the potential difference required to store a unit charge. Analogies between mechanical and electrical quantities. Mechanical system, electrical system. Mass m, inductance L, force constant K, reciprocal capacitance 1 upon c. Displacement is x, charge q. Velocity v is equal to dx upon dt. Current I is equal to dq upon dt. Mechanical energy E is equal to 1 upon 2 kx square plus 1 upon 2 mv square. Electromagnetic energy E is equal to 1 upon 2 q square upon c plus 1 upon 2 Li square. Note that the above discussion of LC oscillations is not realistic for two reasons. Number 1. Every inductor has some resistance. The effect of this resistance is to introduce a damping effect on the charge and current in the circuit, and the oscillations finally die away. Number 2. Even if the resistance were 0, the total energy of the system would not remain constant. It is radiated away from the system in the form of electromagnetic waves. In fact, radio and TV transmitters depend on this radiation. Two different phenomena, same mathematical treatment. Let us list the equivalence between different quantities in the two situations. Forced oscillations driven LCR circuit. M d square x upon dt square plus b dx upon dt plus kx is equal to f cos omega d t. L d square q upon dt square plus r dq upon dt plus q upon c is equal to Vm sin omega t. Displacement x. Charge on capacitor q. Time t. Time t. Mass m. Self-inductance L. Damping constant B. Resistance R. Spring constant K. Inverse capacitance 1 upon C. Driving frequency omega d. Driving frequency omega. Natural frequency of oscillations omega. Natural frequency of LCR circuit omega 0. Amplitude of forced oscillations A. Maximum charge stored Qm. Amplitude of driving force F0. Amplitude of applied voltage Vm. You must note that since x corresponds to q, the amplitude A, maximum displacement, will correspond to the maximum charge stored Qm. A is equal to F0 upon m square into omega square minus omega d square whole square plus omega d square b square whole raised to 1 upon 2. Replace each parameter in the above equation by the corresponding electrical quantity and see what happens. Eliminate L, C, omega and omega 0 using XL is equal to omega L, XC is equal to 1 upon omega C and omega 0 square is equal to 1 upon LC. When you use equations 33 and 34, you will see that there is a perfect match. You will come across numerous such situations in physics where diverse physical phenomena are represented by the same mathematical equation. If you have dealt with one of them and you come across another situation, you may simply replace the corresponding quantities and interpret the result in the new context. We suggest that you may try to find more such parallel situations from different areas of physics. One must, of course, be aware of the differences too. Example 11. Show that in the free oscillations of an LC circuit, the sum of energies stored in the capacitor and the inductor is constant in time. Solution. Let Q0 be the initial charge on a capacitor. Let the charged capacitor be connected to an inductor of inductance L. LC circuit will sustain an oscillation with frequency omega is equal to 2 pi nu is equal to 1 upon square root of LC. At an instant t, charge Q on the capacitor and the current I are given by Q of t is equal to Q0 cos omega t. I of t is equal to minus Q0 omega sin omega t. Energy stored in the capacitor at time t is UE is equal to 1 upon CV square is equal to 1 upon 2 Q square upon C is equal to 1 upon 2 Q0 square upon C cos square omega t. Energy stored in the inductor at time t is UM is equal to 1 upon 2 Li square is equal to 1 upon 2 L Q0 square omega square sin square omega t is equal to Q0 square upon 2C sin square omega t because of omega is equal to 1 upon square root of LC. Sum of energies UE plus UM is equal to Q0 square upon 2 into cos square omega t plus sin square omega t is equal to Q0 square upon 2C. This sum is constant in time as Q0 and C. Both are time independent. Note that it is equal to the initial energy of the capacitor. Transformers. For many purposes, it is necessary to change or transform an alternating voltage from one to another of greater or smaller value. This is done with a device called transformer using the principle of mutual induction. A transformer consists of two sets of coils, insulated from each other. They are wound on a soft iron core, either one on top of the other as in figure, or on separate limbs of the core as in figure. One of the coils called the primary coil has NP turns. The other coil is called the secondary coil. It has NS turns. Often the primary coil is the input coil and the secondary coil is the output coil of the transformer. When an alternating voltage is applied to the primary, the resulting current produces an alternating magnetic flux which links the secondary and induces an electromotive force in it. The value of this electromotive force depends on the number of turns in the secondary. We consider an ideal transformer in which the primary has negligible resistance and all the flux in the core links both primary and secondary windings. Let phi be the flux in each turn in the core at time t due to current in the primary when a voltage Vp is applied to it. Then the induced electromotive force or voltage epsilon s in the secondary with ns turns is epsilon s is equal to minus ns d phi upon dt, equation 45. The alternating flux phi also induces an electromotive force called back electromotive force in the primary. This is epsilon p is equal to minus np d phi upon dt, equation 46. But epsilon p is equal to Vp. If this were not so, the primary current would be infinite since the primary has zero resistance as assumed. If the secondary is an open circuit or the current taken from it is small, then to a good approximation, epsilon s is equal to Vs, where Vs is the voltage across the secondary. Therefore, equations 45 and 46 can be written as Vs is equal to minus Ns d phi upon dt, equation 45a. Vp is equal to minus Np d phi upon dt, equation 46a. From equations 45a and 46a, we have Vs upon Vp is equal to Ns upon Np, equation 47. Note that the above relation has been obtained using three assumptions. Number 1, the primary resistance and current are small. Number 2, the same flux links both the primary and the secondary as very little flux escapes from the core. And number 3, the secondary current is small. If the transformer is assumed to be 100% efficient, that is no energy losses, the power input is equal to the power output, and since P is equal to IV, IPVP is equal to ISVS, equation 48. Although some energy is always lost, this is a good approximation since a well-designed transformer may have an efficiency of more than 95%. Combining equations 47 and 48, we have IP upon IS is equal to Vs upon Vp is equal to Ns upon Np, equation 49. Since I and V both oscillate with the same frequency as the AC source, equation 49 also gives the ratio of the amplitudes or root mean square values of corresponding quantities. Now we can see how a transformer affects the voltage and current. We have Vs is equal to Ns upon Np into Vp and Is is equal to Np upon Ns into Ip, equation 50. That is, if the secondary coil has a greater number of turns than the primary, Ns is greater than Np. The voltage is stepped up, that is Vs is greater than Vp. This type of arrangement is called a step-up transformer. However, in this arrangement, there is less current in the secondary than in the primary. Np upon Ns is less than 1 and Is is less than Ip. For example, if the primary coil of a transformer has 100 turns and the secondary has 200 turns, Ns upon Np is equal to 2 and Np upon Ns is equal to 1 upon 2. Thus, a 220 volt input at 10 ampere will step up to 440 volt output at 5.0 ampere if the secondary coil has less turns than the primary, that is Ns is less than Np. We have a step down transformer. In this case, Vs is less than Vp and Is is greater than Ip. That is, the voltage is stepped down or reduced and the current is increased. The equations obtained above apply to ideal transformers without any energy losses. But in actual transformers, small energy losses do occur due to the following reasons. Number 1. Flux leakage. There is always some flux leakage, that is, not all of the flux due to primary passes through the secondary due to poor design of the core or the air gaps in the core. It can be reduced by winding the primary and secondary coils one over the other. Number 2. Resistance of the windings. The wire used for the windings has some resistance and so energy is lost due to heat produced in the wire I²R. In high current, low voltage windings, these are minimized by using thick wire. Number 3. Eddy currents. The alternating magnetic flux induces eddy currents in the iron core and causes heating. The effect is reduced by having a laminated core. Number 4. Hysteresis. The magnetization of the core is repeatedly reversed by the alternating magnetic field. The resulting expenditure of energy in the core appears at heat and is capped to a minimum by using a magnetic material which has a low hysteresis loss. The large-scale transmission and distribution of electrical energy over long distances is done with the use of transformers. The voltage output of the generator is stepped up so that current is reduced and consequently the I²R loss is cut down. It is then transmitted over long distances to an area substation near the consumers. There the voltage is stepped down. It is further stepped down at distributing substations and utility poles before a power supply of 240 volt reaches our homes.